All right, we're going to talk about arc length, which is basically the length of a curve. And just keep this picture in mind as we go forward here. Just a little bit of history on arc length, if you don't mind. The ancient Babylonians knew approximations for pi and the formula for the circumference of a circle. You see that this is pi and then this is 2 pi, which is really kind of cool. Pi can be estimated empirically by drawing a large circle, then measuring its diameter and circumference and dividing the circumference by the diameter. Nothing we don't know, but haven't known from geometry. Another geometry-based approach attributed to Archimedes is to calculate the perimeter of a regular polygon with n sides, circumscribed around a circle with diameter d. Then compute the limit of the sequence as n goes to infinity. So what you're doing is you're taking a regular polygon and making the sides, the number of sides increase so much as you go to infinity that it almost looks circular. Another interesting factoid from Wikipedia, the Greek letter pi was first adopted for the number as an abbreviation of the Greek word for perimeter. And there's no way I will ever be able to pronounce that, or as an abbreviation for periphery divided by diameter, by William Jones in 1706. The pi is also known as the Archimedes constant, after Archimedes of Syracuse, who provided an approximation for the number during the 3rd century BC, although we really never ever call it Archimedes constant, but kind of interesting to know some history about pi and arc length. All right, well, that's great, but that helps us with circular arc lengths. But what about non-circular curves or curvy curves like x squared and e to the x, because that's certainly more interesting. And before the full formal development of calculus, the basis for modern integral form of arc length was independently discovered by Hendrik van Heuraet and Pierre de Fermat. Yes, and he's the same Fermat as the proof that we are trying to solve. All right, well, the idea basically begins with approximating the length of the curve with n line segments. So we have 1, 2, 3, 4 in this example right here. And then what we do is we choose 4, but we can do a better approximation by having more line segments. And you can see as we would take the number of line segments to infinity that we would actually get the arc length. All right, so as the number of segments increase, the sum of the lengths of the line segments will get closer and closer to the exact length of the curve, which involves a limit, pray tell. All right, so I wanted to talk to you about arc length, but give you a more concrete example. All right, so let's choose a function. Let's say we have f of x equals 4 minus x squared, which is a nice function because it's a nice parabola and it opens down. It's got a y-intercept of 1, 2, 3, 4, and -1, 1, 2, 3. And then we could go to 2, 0 here. So then we want to find the arc length, or the length of the curve from the point -1, 3 to the point 2, 0. Oops, I'm sorry, that's x and y instead of a and b. I wanted to label this point A and this point B. All right, so we could be really inaccurate and, estimate the length of the curve by just using one line segment, and that's going from A to B. And that would be the shortest distance, and so it would be a gross underestimation. Now, how would we figure out that distance? Well, we have to remember what our distance formula is, and we could say that the approximation for the length of this curve, and I'll call it L for length, is equal to the square root of, with the change in x's, which would be 2 minus a -1 quantity squared, plus 0 minus 3 quantity squared, which if we were to do that calculation, we would see that it would be the square root of 18, which we know is a number between the square root of 16 and the square root of 25, between 4 and 5. All right. Now that would be a nice approximation, but we could get better. We could approximate it using 2 line segments. We could go from here to here, and then here to here. And that would be 2 line segments, and that would be a much better approximation. And that would be 0, 4. And then we could go through the process of finding the distance between -1, 3 and 0, 4, and then add it to the distance between 0, 4 and 2, 0. And then we could get better and better by adding more and more line segments to approximate. But let's pretend that we had our function here, and I'm going to zoom in on it, make it really big here, and we're going to zoom in, and I'm going to pretend it's locally linear in this spot. Now, we've always talked about locally linear, meaning that if you zoom in enough on a function, it'll actually eventually look like a line. And I could say that, you know, that length of the line, we could say is ds. We use s for arc length in pre-cal, so let's use s here. And then I could say that using differential math here, we could say that the slope of this line is going to be the change in y, which will be the small change in y over the small change in x. And that's how you would get from the end here to the line here to the top of the line here. And it would be dx over dx and up dy. Well, that forms a nice right triangle here. Mathematically state that ds is equal to the square root of dx quantity squared plus dy quantity squared, using Pythagoras. And I don't think that's much of a stretch for everybody. But this is where the magic happens. And I know you love it when we say magic. All right, I'm going to make the square root a whole lot bigger, and I'm going to factor out a dx squared out of this expression here. So dx squared, and what's left is dx squared over dx squared, because I'm factoring out a dx squared, plus dy squared over dx squared. And when I do that, this is clearly 1. And I could rewrite this as the square root of, this turns into 1 plus dy dx squared. And I could actually take the square root of my dx squared, and that would just be dx on the outside here. And that would just be the length of one of the little lines that we would be connecting. All right, but I don't want the length of just one of the lines. I want the length of all of the lines. So since we're going to use some calculus, we could say that the sum is going to be, because this is for one length, the integral from, we'll say, from A to B, this will be the arc length, or the big arc length, which we'll call S, is equal to the integral from A to B of 1 plus dy dx quantity squared dx. And in calculus, we call that length of curve. So it's usually written as L equals the integral from A to B of the square root of 1 plus dy over dx, the derivative squared dx. All right, so it's derived from a little bit of calculus. I mean, Pythagoras up here, which is really kind of cool. So let's do an example. And I'm going to do number 12 from your book because we like to do some examples from the book here. So let's say we want to find the arc length or the length of the curve of y equals x to the 3/2 from x equals 0 to x equal 4. All right, so in order to do that, we have to find f of x is equal to x to the 3/2, and we need to know what f prime is, or dy dx, and that's going to be 3/2 x to the 1/2. So we know the derivative, and we just plug it into the arc length formula. So the length is going to equal from 0 to 4 the square root of 1 plus 3/2 x to the 1/2 quantity squared dx. All right, so let's simplify that, and we get L equals the integral from 0 to 4 of the square root of 1 plus 9 over 4 x dx. And we can use u sub here because it's a linear term in here, so we can say 1 plus 9/4 x, and then du is going to be 9/4 dx. And we don't have a 9/4 in the integrand here, so we'll multiply this by 4/9. Du will be the nice substitution for dx, and so we'll say 4/9 times the integral of u to the 1/2 du turns into 4/9 u to the 3/2 times 2/3, and that's going to be 8/27 u to the 3/2. So I'm going to bring it back to my integral here and say that this will be 8/27 times, well, what is u? U is 1 plus 9/4 x to the 3/2 evaluated between 0 and 4. All right, so let's plug in 4. What happens when you plug in 4? This becomes 1 plus 9, which is 10, to the 3/2. So we're going to have 8/27 times 10 to the 3/2. And when you plug in 0, that's just going to be 1. And 1 to any power is just 1. So this will be 1. And so our answer is going to be the length of that curve from 0 to 4 is going to be 8/27 times 10 to the 3/2 minus 1 units. That wasn't too tough. If you know the formula, it's pretty simple to do. But I know your question's going to be, oh, Mrs. Muller, that's an easy one. You're not going to give us one that easy. Well, let's do a challenger. Let's do a challenger question. How about this one? Let's say we have a function y equals the natural log, because you guys love logs, of cosine of x. All right, and we want to find the length of the curve between 0 and pi over 4. Well, I don't know what that looks like. Well, I took the liberty of graphing it ahead of time before I did this, but we'll show it to you on Desmos here. So we'll say y equals the natural log of cosine of x. All right, and we're going to go between 0 and pi over 4. All right, so let's put in x equals pi divided by 4 so we can see that line, and I'm going to make it dashed here. So we just want to find the length of the curve here from 0 to pi over 4. All right, now if we had to estimate what this length would be, we would know that it has to be greater than pi over 4. And so that's kind of a nice thing to know before we start. So everybody got the picture of that graph in their mind? Or I'll just leave it up there. Okay, so we're going to try to find the length of this curve, and this is pi over 4, so we know it's going to stop there. Okay, so what do we need to know? Because we have the formula, L equals square root, the integral, I'm sorry, of the square root of from a to b of 1 plus dy dx, quantity squared dx. So we need dy dx, which is a nice little refresher of the derivative of a log, which is 1 over the function. So it's going to be cosine of x on the bottom times the derivative of cosine, which is negative sine of x, which is simplified to negative tangent of x, which is actually going to be really helpful here in a minute. All right, so we're going to just plug it in the formula. We're going to say the arc length L equals the integral from 0 to pi over 4 of the square root of 1 plus, and I'm going to square negative tangent, which gives us tangent squared x dx. Now, I can't integrate that, but boy, 1 plus tan squared x. Wonder what that could be. Well, let's recall that 1 plus tangent squared x, using our Pythagorean identities from trig, is equal to secant squared x. So we can say then that this is going to equal the integral from 0 to pi over 4 of the square root of secant squared x dx. And that's just going to be the integral from 0 to pi over 4 of secant x dx. Now it's really the absolute value of secant x. But anyway, we know the antiderivative for secant x. It's one of those where you have to multiply by that seemingly bizarre factor of 1. And so we know that when we do that, we're going to get the natural log of the absolute value of secant x plus tan x evaluated between 0 and pi over 4. And when we evaluate that, we get pi over 4. The secant of pi over 4 happens to be root 2. So this is going to be the natural log of absolute value of root 2 plus 1 minus the natural log of, well, the secant of 0, believe it or not, is 1, and the tangent of 0 is 0. So this turns out to just be the natural log of 1, which goes to 0. And so our answer is the natural log of the absolute value of root 2 plus 1. All right, and I was telling you that we felt like it would be somewhere between, there would have to be greater than pi over 4. So I just happen to have my handy dandy calculator here. And I am in radians, which you should be in. Focus here. All right, so let's do that calculation. We want to take, I'm going to show you what pi, let's clear this out, my home screen. F1, 8, clear home. And let's do second pi divided by 4 to see what that equals. Well, obviously equals pi over 4, but it's about 0.785. So we know that's the low end. So we got to figure out what the natural log, so we'll say natural log, which is second natural log of second square root of 2 plus 1. And we want to know what the approximate value is. So we can say that our answer is approximately 0.881 units, and using AP Calculus digits, we have to have 3 decimal places. And so that's certainly reasonable because it needed to be greater than the pi over 4 number. Okay. Well, let's do another example. So far, so good. How about we do a simple trig function? Let's say we want to find the length of the curve, the arc length of y equals sine x between x equals 0 and x equals pi. Now, we don't need a calculator to graph that one. That one we know pretty well, or at least I hope we do. That's going to be the sine curve that goes from 0 to pi. So if we were guessing at an estimation, we would know that the arc length would have to be greater than 3.1415 and change, just because, you know, this length here is 0 to pi. We know that's pi. All right. So in order to find the arc length, we have to go from a to b of the square root of 1 plus dy dx, quantity squared, dx. And so we need dy dx here. So what is dy dx? Well, dy dx is just cosine x. No big deal. So we'll say the arc length is equal to the integral from 0 to pi of the square root of 1 plus cosine squared x dx. Well, we look at that and we say, the only thing I could possibly do is let the inside here be u, but du would be power down function log of power 1 to 0 to the inside, 2 cosine times negative sine, and I don't have that anywhere in the integrand. And believe it or not, arc lengths sometimes are very pesky integrals that are very difficult to integrate. And this is not an identity, because it would be, if we used 1 minus sine squared, that wouldn't help us any. So we have to use our calculator on this one, believe it or not. So here we go. This is just a review on how to integrate with the calculator. How do we do that? We do second integrate, second square root, 1 plus cosine x, close the cosine, to the second. Now we have to, when we're integrating cosine with the calculator, we don't have a vehicle to put the square in here, so we have to put the square on the outside. So now I have to close the square root. There it is, comma, with respect to x, comma, from 0, comma, to second pi. Now we already said we're expecting an answer that's greater than pi. So let's see what we get. Oh, it's busy, it's thinking. There it is, approximately 3.820 units, which is a little bit bigger than pi. All right, so our calculator saved us that time. All right, another trick on finding integrals or arc length is sometimes we're not going to do it with respect to x. Sometimes we're going to do them with respect to y. Okay, which is not a problem. We're not going to freak out about it. The only thing that changes is, instead of the arc length formula being from A to B, we're going to go from C to D, because that's what y would go to and from. And it's still the square root of 1 plus, and now we're going to switch the derivative around, and we're going to differentiate x with respect to y and square it, and then integrate it with respect to y. And the same little Pythagorean proof to get this formula would apply. Instead of factoring out a dx squared, we'd factor out a dy squared and get the same formula. Okay, so let's do an example. Let's say I'm given x equals 1/8 y to the 4th plus 1/4y squared. And I want to find the arc length from 1 to 2. All right. All right. So I've got x as a function of y, so I need dx dy. So I'm just going to take the derivative, dx dy. Now this is going to be power down function lower to the power 1. That derivative is going to be 1/2 y to the 3rd. That's not bad. And then minus, now I'm going to you can rewrite this as 1/4 y to the minus 2. So if I take the derivative of that, that would be minus 1/8, or no, let's see, minus 1/2, I'm sorry, y to the negative 3. But I need to square that, and I don't want to have to square it under the integrand, so it could be a little bit messy. So let's square it here. So dx dy quantity squared, I do that sometimes to make things easier, is equal to, now I have to square this, which means we're going to do this squared plus this squared times this times 2, right? And I add that. So when I square this, I get 1/4 y to the 6th. And then I'm going to multiply these together and multiply them by 2. So if I multiply these together, I get 1/2 times negative 1/2, which is negative 1/4 times 2, which would be negative 1/2 times y to the 3rd times y to the negative 3, which just turns out to be y to the 0. So I just have negative 1/2 hanging out here, plus this squared, which would be 1/4 y to the negative 6th. It's pretty messy. Pretty messy. All right. But what we're going to do now is do the integral. So L equals integral from 1 to 2 of the square root of 1 plus, and I'm going to put this in here because I already squared it, 1/4 y to the 6th minus 1/2 plus 1/4 y to the minus 6 dy. That's pretty messy looking, but let's see what we can do about adding like terms, because this and this here can add. So we'll say the integral from 1 to 2 of the square root of 1/4 to the 6th, or y to the 6th, plus 1/2 plus 1/4 y to the negative 6 dy. Now, this turns out to be a perfect square under here. It's similar to this one, but this is going to turn out to be 1 to 2 of the square root of 1/2 y to the 3rd. Instead of minus, it'll be plus 1/2 y to the negative 3 quantity squared dy, which is a little bit of a miracle. And then when we take the square root, it'll be absolute value of 1/2 y to the 3rd plus 1/2 y to the minus 3 dy. And we can integrate that, which turns out to be 1/8 y to the 4th minus 1/6. No, 1. I'm going to raise that 1, so it's going to go to the minus 2. So minus 1/4 y to the negative 2, going backwards in my brain, evaluated between 1 and 2. And let's plug in the numbers and see what we get. We get, that's going to be 16 over 8, which is 2, minus, this is going to be 1 over 2 squared is 16, 2 squared is 4, but that's 1 over 16 minus, I plug 1 in, I get 1/8 minus 1/4, which I happen to do ahead of time, and it works out to be 33 over 16 units. I'm not going to bore you with the math calculation. So that would be the length of the curve. And that's with respect to y. One last tricky situation, best for last. Let's do number 28 from the book because it's kind of an interesting one. And the relation or the function we have is the square root of x plus the square root of y equals 1. Now, what's interesting about this function here is when x is 0, y is 1. I'm going to just put a 1 here. And when y is 0, x is 1. All right, and x and y have to be positive numbers, so it can only be in the first quadrant. And so this curve basically lives between here and here. Kind of a fun looking curve. Except something interesting happens. If I want to find the length of this curve, and I'm going from 0 to 1, I have a problem here because what is the slope here? What is dy dx here? Well, guess what, folks? It's undefined. And when we have a curve that is undefined in the slope arena, we can't integrate from 0 to 1 if dy dx is not defined at one of the locations. All right, so sadly, we can't do that. So I suggest we have to go halfway and multiply it by 2. Well, how do we figure out what the halfway point is? Well, the halfway point, which is interestingly enough in this function, when y equals x. So to find the halfway point, we're going to let y equal x. And well, the way I solved this was I let, we're going to integrate with respect to y. So when I integrate with respect to y, I'm going to take my equation, square root of x, square root of y equals 1, and I'm going to plug in square root of y plus the square root of y equals 1. And we're going to get 2 root y equals 1, root y equals 1/2, and that's y equals 1/4. Okay. And so I know that halfway is going to be 1/4, 1/4. Okay. So we need to also solve for x to integrate with respect to y. So we're going to take the square root of x equals 1 minus root y. X equals 1 minus root y quantity squared. And I need to find dx dy, which is going to be, well, that's the chain rule. So power down, function, lower the power 1 times the derivative of the inside, which is negative 1 over 2 root y. Okay, these 2's cancel, and I'm left with, I'm going to absorb the negative here and go square root of y minus 1 over root y. That's dx dy. All right. So we're going to find the arc length, and we're going to multiply it by 2 because that's not defined there. And then we're going to go from 1/4. Y goes from 1/4 to 1. The square root of 1 plus dx dy squared, which would be the square root of y minus 1 over the square root of y squared dy. And we're going to use our calculator to figure out that. So it'll be 2 times the integral of 1/4. 1. Let's simplify this a little bit. This will be 1 plus square root of y minus 1 quantity squared over y dy. All right. So let's see what we got. Here's the calculator. Clearing that out. All right. I'm actually going to go 2 times second integral of second square root 1 plus parentheses second square root y minus 1 close square divided by y close the square root comma y comma 1 divided by 4 comma 1 and close that integral, and let's see what we get. All right, and that's the right answer, which is about 1.623 units. Now, the reason we had to integrate with respect to halfway is because this derivative was not defined. But if I integrate with respect to y, then that slope is actually 0. Now, we could have integrated it this way if we went from 1/4 to 1 and then done dx dy, and we would dy dx, and we would have gotten the same answer. All right, so that's all I have for you on arc length, and hopefully you were able to follow it, and we will chat with you later.